Hello, this is a short demonstration about a useful function where we can consider failure index rather than simply as a constraint. We can consider a range that failure index is allowed to work within. We'd look to minimize within that range whilst also minimizing mass, but we give ourselves a little bit of flexibility so we can identify which, if any, load cases are becoming problematic and which ones are being solved quite easily. So we're doing this on a Formula 1 chassis, and here we're looking at some of the new rules that are actually quite severe for the side. This is an old chassis, but the load cases are fairly up to date. So here we've got a side load applied with pressure pads at 6 different locations, and then we have some stiffness cases and several other strength cases over the chassis. So if I just take a look at this, for example, in the side case, you'll see we also have some contact defined, which is completely acceptable to solve with. And if we want to look at another tip whilst we're in this demo video, if you are optimizing for contact within Genesis, a useful setting is to go to your Design tab, Advanced Options, and set these parameters here, CNT, DC and IT, so definition and iterations. And what this will do is it will mean every 5th iteration, a full contact iteration will be performed, and in all the other stages, so every sort of 2nd, 3rd, 4th, it will only perform 1 iteration and just continue from the previous converged state. So that solves a lot faster for your contact problems. So if we look at the formulation of this optimization, then we'll see we have already a minimized mass, which is of the composite parts. We then have some displacement constraints. So this has already been prepared for an optimization for topometry. So you can see here the composites have been designed for topometry, ready to go. So this demonstration is not really teaching you those areas. It's now teaching you how to add the failure index as this combined constraint and objective function. So in Genesis 19, this is done using what's called a Lua script, and we can get to that if I just go here. And you'll note I've already navigated to this Lua scripting function, and also you'll see I have a lot of these for various different functions that I use to post-process or pre-process models. And I've already got this defined, which is to minimize beta failure index. So what I'm going to do is just show you how to create one of these to add it for the first time. So to add it for the first time, we go to the plus at the bottom, and this allows us to populate a script, and it will just save this into a user folder for you for future reference. So I just navigate to Notepad++. This is the script that you'll need to do this function, and this is easily obtainable from our support team at support@grm-consulting.co.uk. None of this is needed to be edited except for this first line here, which is the load cases we would like to apply our failure index to. So what I'll do, I'll just add the script first of all. So we basically select all and copy, and then we move back to our scripting page, and we just simply save this or paste this in, and then give it a min beta failure index. So I would save and close here. I won't do this because I've already added it to my session, but that once that's done will appear in your list here. And then the next thing we want to do, so to use this, we can just run it on models multiple times. But what we need to do is confirm the load cases that we want to apply this to. So in my particular example, I'd like to run it from here, 5, 7, 10, and through down. So what I'm going to do is just temporarily edit the script to match this particular model. So min beta phi, I'll edit that. Okay, and because this is a demonstration where I've done it already, you'll see I've already typed these in. So it's very easy to do. You just enter them as you want to, and then save and close. And with that in place, the next step is just to run that. Note that this is going to work on all visible pcomp properties. So if you do want to exclude some areas from the model, then that's no problem at all. You just simply hide them from the display prior to running this script. So that's now run, and we'll take a look at what we've got created in our design data. So first of all, in the objective, we now have a beta objective function created for each load case. So you can see that's active for each load case. We still have our mass, and this is something that's you may tailor yourself, but I would certainly strongly recommend that you then adjust the weighting factor on your mass to match the number of load cases that you have in the beta. So they have basically an equal weighting between the failure index contribution here, 16, and my mass here of 16. Okay. Next, I can just check the constraints, and so you can see we also have now these beta constraints. So these are present for several for each load case. In this particular model, it ended up with a total of 6 per load case, and all that's doing is breaking it down into groups of pcomp properties that have a common number of plies. It's a quirk of Genesis's constraints, but this is all taken care of in the process. So with those in place, the important thing to consider here is what we have defined for our design variables. Excuse those were there. Those are from the previous setup before I started this recording. So we now have one beta design variable per load case. And if you look at this, the default in the range is 0.1 to 1. And what that's going to do is that's going to ask Genesis during the optimization to ensure that the failure index is below 1, but it will also then try to minimize that failure index down to 0.1. And that's a bit extreme really for what we want to do. We want to make ourselves a sensible range. So we can do that by modifying these design variables. And what I'm going to do for this, and I find this is quite a good range to use, is I will give myself a value a little bit higher than my target, because in the optimization there might be some areas I can just identify and resolve manually myself later. And then a lower boundary, which is what I really would like to get to, so 0.8 in this case. You can change these yourself, but I certainly would recommend these settings. If you ensure these are checked at lower bound, upper bound, then you'll find that that's updated for each design variable and therefore each load case. Okay, so that is the setup. It's as easy as that. I will go ahead and run this. Be aware that anything that has this many failure index constraints needs to be running on a large model, and we really want to large computer system, ideally Linux, and be prepared it will take a fair few hours to solve. Okay, so I'm just going to pause this whilst I run it. Okay, so I've now run the job. I should imagine this has taken a little while. That was I think this was around about 8 hours to solve this on our cluster. But we'll take a little look. So I've imported the results, and what we can take a look at is most interesting if I just turn that filter off. If you're not familiar, if you want to filter results, you can just simply type that in here and it will filter results types, makes it easier to select things. And again, what I'm just going to do is change my display to be only pcomp properties, and I'll just clear all the load cases. So now I can start to look at the failure indices I've achieved in each load case. 0.8, 0.5. So these are actually well under even our 0.8 limit for these lower cases. But if we go through to the ones we know are of interest, these side pushes are very difficult. You can see we're at 1.2, which is the maximum allowable on the maximum failure ply, which is what I've considered. And then the others at 0.82, 0.81, and then these lower ones are at 0.8. So that's quite interesting to see. And you can get a much clearer visual look or sort of tabulated summary of this by looking at the HTML file that is generated by Genesis during the solve. Now this file is created actually and updated during an optimization, so you can load this at any point in an optimization to get a summary of the status. But what we have here is the first line Here is our mass, so these are the components of our objective, and here we've converged on a mass of 37.5 kilos. And if we then look at these other ones, the second field is our load case, so these correspond to those design variables that we've added to the objective, so 1 through 16 that we had created for each load case, and this is showing the status of what they've been reduced to. So you can see that in most cases the design variable has been moved down to 0.8. Down in these side push cases you can see that clearly that this load case 19 is the one that has worked the hardest, and it's found that basically there's a trade-off between weight saving in the current geometry and failure index. It's saying, do you know what, I'm better to just compromise this failure index a little bit at the expense of, or for the benefit of, getting this good and efficient mass. And that allows you to understand that that is a driving force in the optimization, and therefore you can maybe look at geometry changes to improve the structure in there in a more efficient manner. Okay, so that's the approach. The rest of the optimization is common to other composite optimization, and thank you very much for watching.